Okay, so welcome everyone. It's my great pleasure to introduce today's speaker, Johanna Erdmenger. So she's actually a high energy physicist, but she has roots in low energy physics, as I just learned 5 minutes ago. So she did a diploma thesis in superconductivity. After that, she went for a PhD to Cambridge, which also came with switching the topic. She then did postdocs in Leipzig, MIT, and had a Eminöter group in Berlin. Afterwards, she moved to Munich, where she had a position at the Max Planck Institute, and now since a couple of years, she's in Wuerzburg, which is actually my home university where I studied. And yeah, so I'm really happy to have you here as a speaker. And so the title of the talk is Turbulent Hydrodynamics in Strongly Correlated Kagome Metals, and the floor is all yours.
Yeah, thanks a lot, Lars. So thanks a lot for the kind invitation to this very interesting seminar series, and I'm very glad I learned about this video page as well, which is super helpful. And I will certainly spread it among people. Okay, so today I'm going to tell you about about a collaboration between people from a more high energy physics, ADS-CFT quantum field theory background, like myself, with our colleagues from condensed matter in Wuerzburg. And as you of course all know, Wuerzburg is rather famous for its condensed matter physics. So, and it's very nice that we were able to set up this collaboration between different fields. So the talk is entitled Turbulent Hydrodynamics in Strongly Correlated Kagome Metals. And so there's a lot of words in this title. And so I will take you through the various steps that are involved in this project. All right, so I have to, sorry, just shift this one bar. Because, okay, so the motivation and the background is that I look at hydrodynamics rather from a perspective of the ADS-CFT correspondence. And so as you may have heard in the meantime, maybe many times already, so the first really successful application of the ADS-CFT correspondence, which is a relation between gravity and strongly coupled quantum field theories, was in fact in the context of hydrodynamics, and hydrodynamics applied to the quark-gluon plasma, where there was this very famous result for the ratio of the shear viscosity over the entropy density, which was calculated by Koftu and Sonne-Starinets in 2004. And they found this rather small number here, 1/4 pi, and these rather simple units, h bar over k Boltzmann. And so actually this result has been experimentally confirmed in the context of the quark-gluon plasma and of heavy ion accelerators, for instance, the RIC accelerator, and also at CERN. And so this was obviously a breakthrough of using these methods, which actually come from string theory, quantum gravity, to describe something in the real world. And now, of course, there's this important question: if there's further applications of this in the context of hydrodynamics, also to electrons in solid. And so I'm investigating applications of ADS-CFT also in this context. So I should mention the funding, which comes from two big collaborations that we have here in Wuerzburg. One is the Collaborative Research Center dealing with topological materials. And then more recently, we also have this excellence cluster in the German Excellence Initiative, together jointly with our colleagues in Dresden, also on complexity and topology in quantum matter. Okay, so today I'm going to tell you about this collaboration between ADS-CFT and condensed matter physics, which led to the project which gave the title to the seminar. And let me just introduce our collaboration. So there was Domenico Di Sante, who is actually in the audience right now. So thanks for joining, Domenico. And so there are Martin Greiter and Ronny Tomale here from Theoretical Physics 1 in Wuerzburg. Yannis is my student who's just graduating, will have a postdoc in Genova. René Meyer is in our ADS-CFT group as a lecturer. And David is also in the audience. He was our postdoc in Wuerzburg and now moved to Leiden. And so he gave a talk in the same seminar series in March. And then we also collaborated with two researchers from Bremen University, Erik van Loon and Tim Wheeling, and I will mention where they entered into this project. So this paper was published in Nature Communications in last August. And the same essential idea is that we propose a new Dirac material which has stronger electronic coupling than graphene. So the name of this putative material, so I should emphasize right away that it hasn't been synthesized yet, is the so-called Scandium Herbert-Smithite. I will explain in some detail what this is. And so the idea to do this is to find enhanced hydrodynamic behavior of the electrons for reaching even smaller ratios of this ratio of the shear viscosity over entropy density, which, so as I mentioned, in the ADS-CFT context was found to be 1/4 pi in the absolute infinite coupling limit. And graphene, of course, is a relatively strong coupling, but still quite some way away from absolutely infinite coupling. So in view of reaching even smaller values of this ratio, it would be nice to have a material with a much stronger electronic coupling. Okay, towards the end, if I have time, I wanted to briefly mention two other projects which we did here in Wuerzburg and which involved David Rodriguez. But yesterday, when I prepared for this talk, I found out that he actually talked about these papers already in March. So I will be extremely brief, but maybe I should mention them at the end. And so there, it's also about hydrodynamics for electrons in wires. And here we had also a collaboration with my colleague Evelina Hankiewicz, who's also a condensed matter physicist in Wuerzburg, and her group. Okay, so as compared to the quark-gluon plasma, of course, hydrodynamics for electrons is a much more challenging state of matter to be realized. And okay, so it requires really that phonons and interactions with impurities have to be suppressed. And if that's the case, then the effective electron-electron interactions may lead to a hydrodynamic electron flow. And in fact, in a typical material, there's only a very small parameter window where this can happen. So the electron interaction scale must be shorter than scales for the interactions with phonons, impurities, or walls. So here you can see all these scales. So this is the electron scattering mean free path. This is the impurity length, the phonon length, and the width of the channel. And for having a necessary condition for hydrodynamic behavior is precisely this relation here. So this has already been studied for quite some time. And so actually in the very first seminar talk in your series was by Igor Naroshny, and I think he mentioned this already some time back. So let me just very quickly mention this. In particular also because this is an experiment done by my Wuerzburg colleague Laurens Molenkamp. Also, when listening to the talk again, people often say that this experiment was done in 1984. But in fact, it's done in 1994. So there's sometimes, I have heard this now a couple of times, that people predate this by 10 years. It's really from the 90s. But what they measured is the decrease of the differential resistance, dV by di, with increasing current I. And that's a clear sign of hydrodynamic behavior, as I will show briefly. And so their measurements in gallium arsenide, which is a very weakly coupled material. But as we will see, in general, hydrodynamic behavior is much more pronounced at stronger electronic coupling. And then, of course, so far the material of choice is graphene, as you all know very well. And so there should be lots of examples here, also giving the audience. But I just put this one here, which is this negative local resistance that is found in graphene as an indication for hydrodynamic behavior there. So let me very briefly tell you about this Molenkamp and the Young experiment, which goes back to some proposals by Gaugy already from 1968. And so, in fact, there's two possible regimes. One regime when the electron-electron scattering length is larger than the width of the tunnel, then we are in the so-called Knudsen flow regime, which is more the ballistic regime. And so the dominant effect is scattering of the walls. And on the other hand, in the Poiseuille regime, which is in fact the hydrodynamic regime, the electron-electron scattering length is less than the width of the wire. And then this is where hydrodynamic behavior sets in. And in the experiment, this is seen by looking at this differential resistance. And in the Knudsen flow regime, actually, the resistance grows with increasing current. And then when the Poiseuille flow, so the hydrodynamic regime sets in, and then actually there's a decrease, which then leads to a maximum, which is the so-called Gaugy effect. And so this was observed in these papers, that this is actually experimentally the case in these materials, which is a nice indication of hydrodynamic behavior. And so I should say then, when we do ADS-CFT and also hydrodynamics in the context of ADS-CFT, we are always well in this regime of this Poiseuille behavior. So the ballistic regime is something which is not so easily accessible to ADS-CFT because then the coupling is not strong enough. Okay, so now for hydrodynamic behavior, one would like this scattering length to be really small. And so as is known from various calculations, which I refer to also a little later, essentially at very tiny scales, this is proportional to 1 over the effective electronic coupling squared. And so this means that when the coupling becomes larger, then this becomes smaller, and this is more will lead to more robust hydrodynamic behavior. Now, the effective coupling, I'm sorry, there's a slight problem because I can't see the first line of my slide due to some strange bar, which I can move it. Okay, so that's good. So now it's better, sorry about this. So the effective coupling is actually E squared over the dielectric constant, dielectric parameter, and the Fermi velocity enter here. So to see more robust hydrodynamic behavior, then in general, we would like this coupling to be rather large. Okay, so as I already mentioned, the material of choice to look at this hydrodynamic behavior so far is graphene, which I expect you are all very familiar with, and it has also this nature of being very pure. And it's a Dirac material, which leads to a linear dispersion relation. And this is very interesting in the context of ADS-CFT because this linear dispersion relation leads to a quasi-relativistic behavior here in the vicinity of the Dirac cone. And so this is something extremely useful also in context of using hydrodynamic behavior. Okay, so let me talk a little bit more about the coupling range in hydrodynamics. So, and it was already found some time ago that the effective Coulomb coupling grows logarithmically as a function of the temperature. And it's of order 1 in the hydrodynamic regime. So this is already a result due to Song from 2007. And then there's a very nice analysis by our today's host, Lars Fritz, and with Jörg Schmalian and Sumir Sachev and Müller about using kinetic theory. And they explored this quantum critical behavior of graphene in the mu-T plane. And essentially, they found that eta over S scales like 1 over alpha effective. And so in generally, in the quantum critical region has this logarithmic behavior. However, outside the critical region, it goes with 1 over T cubed. And so this was an important input here also for our analysis here. Okay, so as I mentioned, if we use ADS-CFT, then it's very convenient to be in this quasi-relativistic situation. And then we can use relativistic hydrodynamics, which means that we expand the energy momentum tensor, for instance, in 4 velocity derivatives. So 4 velocity is this relativistic velocity, which is a 4-component vector, 1 associated with time and 3 associated with space. So this is this vector u here, and mu in general will go from 0 to 3. So 0 is the time component, 1 to 3 are the space component. And so for an ideal fluid, so then we take hydrodynamics to be this effective field theory of long wavelength fluctuations. And so this means that the more derivatives there will be, then the more higher order behavior we will. So I would say that the derivatives are a natural expansion parameter if the fluctuations are a very long range. And so for an ideal fluid, then we have this behavior here with the energy density and the pressure. And then at higher order viscosities and so friction will appear. And so this expansion goes to all orders and derivatives in principle. And in the first order term, this is written out here in this relativistic notation. So we see derivatives of our 4 velocity. And so this is the transverse traceless part. And this is the trace part. And this coefficient is actually the shear viscosity, and this is the bulk viscosity. So generally, when we have critical or conformal behavior, then because the energy momentum tensor will be traceless, this coefficient will be 0. And so the coefficient of interest is really this shear viscosity that we have here. So this P here is just a projector which involves the Minkowski metric and the 4 velocities. Okay. Okay, since there are many condensed matter physicists in the audience, I think I should explain just a little bit how this calculation of Coulomb-Coupling worked, how they actually managed to find this very nice result for the shear viscosity. So they calculated essentially this coefficient here. This is a coefficient that enters the energy momentum tensor. And so this can be calculated using a Kubo formula. And so what they do, they look at the propagation of a graviton field, which is a metric 2 tensor, which couples to the energy momentum tensor, and then propagates in this anti-de Sitter space with a particular action, which is the so-called Einstein-Hilbert action that is written here. So it's an action in 1 dimension higher, which involves the Ricci scalar. And because ADS is a hyperbolic space, there will be a negative cosmological constant term here. And so in this case, the dual field theory that is described in the setup is an SUN gauge theory at infinite coupling. So n goes to infinity. This is, of course, always something we have to deal with later when we go to condensed matter physics, because in condensed matter physics, we definitely don't have an SUN gauge theory. But the interesting point is that the so-called 't-Hooft coupling, which involves the coupling of the gauge theory, which later will be our alpha, and this n will also be, this will be very large. Okay, and in this approach, these authors actually found this very nice result. So now in the new paper that I will present to you in this talk, we will look at corrections to this result. And in particular, we will look at the leading correction in the inverse 't-Hooft coupling, in the inverse strong coupling expansion. And actually, we will find that the leading term in our case will be lambda to the -3/2. And to obtain this result, we need to actually look at terms of 4th order in the curvature contributing to this gravity action. But I will explain all of this in more detail later on. Okay, first let me again give you a little more detail about how this shear viscosity was calculated originally, so how this result was found. So the energy momentum tensor is dual to a graviton field, so a propagating metric. And so how to obtain the shear viscosity is to calculate the correlation function, the 2-point correlation function of these off-diagonal elements of the energy momentum tensor from the propagation in an anti-de Sitter space, which contains a black hole. And then the shear viscosity is obtained from a Kubo formula. So this is a Kubo formula of the type that you know very well from linear response theory. And so this retarded Green's function actually enters via this 2-point function here. And so this calculation then just gives this result for the shear viscosity. But then to get this universal behavior, which doesn't depend on this large number n and not on the temperature, it's convenient to form this ratio with the entropy density, and the entropy density is given by the horizon of this black hole, which is placed in this gravity space. And so then finally one gets this result that I advertised before. I should mention that from the quantum critical behavior, where the dominant time scale is h bar over k Boltzmann t, one can already infer that this dependence on h bar over k Boltzmann. And the new result of the ADS-CFT calculation is really this 1 over 4 pi here. Okay, so the final thing I want to say about how to calculate these retarded Green's functions is that this black hole space gives us for free a causality structure, which then gives us a very simple realization of retarded and advanced Green's functions. Okay, so we look at some operator here. So I should say this blue line is the boundary of our space. So that's where we consider this energy momentum tensor or general operator O. So in the example I considered before, this operator O was the energy momentum tensor. And then here we see a so-called conformal diagram of a black hole. So where the extra direction of the ADS-CFT correspondence that is added to our normal space in which we work points in this direction, and time essentially goes in this direction. So then if we throw something into this black hole geometry, it can only travel to the future and then fall into the black hole. On the other hand, if something leaves this past horizon at some previous time, then it will reach us in finite time here where we sit. And so the fact that here we have to impose boundary conditions at the horizon, then for free gives us either a retarded Green's function from this fluctuation and an advanced Green's function from this fluctuations. So the boundary condition that we impose on this horizon fixes the causality structure of our correlator that we calculate in this space. All right, I think now I will completely change gears and talk about condensed matter physics. So would anybody like to ask a question about this before I move on? So have you seen this before? Is it? Yes.
I don't see anything in the chat neither. So
okay.
It seems to be.
Let me just, everybody seems to be happy. Okay, then I expect you have seen things before. Good. Good. So now let me talk about something else. But of course, the idea will be then to combine these things together. All right. So let's look at Kagome materials. And so this name Kagome comes from the Japanese language, and is a particular Japanese basket weaving pattern, as you can see here in this picture. And so these materials, Kagome metals that have this particular lattice structure in 2+1 dimensions, were actually first synthesized in 2018 in a particular alloy with iron and tin. And they show lots of very nice physical properties that are of interest to condensed matter physicists, such as ferromagnetism, spin frustration, topological structure, non-zero Bailey phases, a quantum Hall effect, and also Dirac fermions. So these things are, of course, very popular these days. And I should mention, though, that there is actually a Kagome material that is present in nature, which is the so-called Herbert Smithsonite. I think this is called after an American mineralogist who discovered this. And so this is a material that really exists. So this is a photo from Wikipedia, and it consists of zinc, copper, oxygen, hydrogen, and chlorine. And this material also has this hexagonal structure, which you can see here. So now I will tell you the basic idea of the paper that I'm advertising here, and which actually makes a connection between condensed matter physics and the ADS-CFT correspondence. So the punchline is actually the following. So this original Herbert Smithsonite, if I just show the chemical composition again, has this zinc here. And zinc is a twice positive element. And in this original Herbert Smithsonite, actually, the Fermi surface is below the Dirac point. So very schematically, if you have a Dirac structure, a band structure, the Fermi surface is somewhere here. And so this is not really a Dirac material. And now the idea that we propose in this paper is to synthesize a material where this zinc is replaced by scandium. And scandium is an element which is 3 times positive. And this change, so this means really replace all the zinc atoms by scandium atoms. And if this is possible, this will place the Fermi surface exactly at the Dirac point here. And then we do actually have a Dirac material. And so we can apply all this relativistic hydrodynamics. So that's the punchline of the paper. And now let me give you some more details. Okay, so first of all, here's a picture of this Scandium Herbert Smithsonite, which is, so you see this hexagonal structure. And so the gray atoms are originally the zinc atoms, which we propose to replace by scandium atoms. And so the green is the chlorine, the blue is the copper, and the red is oxygen, white is hydrogen. And so the material that we suggest is to replace these gray atoms here. Okay, so now our colleagues from condensed matter, and also importantly Domenico Di Sante, who is in the audience, they did a thorough condensed matter analysis of this new suggested material, and they calculated both the band structure and some ab initio calculation, and also the phonon dispersion relations. And so here, this is the picture which you can find in our paper. Now, as you see, it's a Dirac material. And so the fact I would like to draw your attention to is that the opening angle of this cone here is now much wider than what you would have for graphene. So graphene has this much narrower cone. And in this new material, the opening angle of this cone is much wider than before. So that will play an important role. And also the analysis of the phonon dispersion shows that the material should actually be stable, and also in the hydrodynamic regime up to a temperature of about 80 Kelvin, which of course would be very handy for experimental measurements of hydrodynamical behavior. And so we also expect hydrodynamic behavior to be much stable in a rather broad temperature regime here. Okay, so this is the result of our colleagues from the condensed matter participants in our collaboration. So the important parameters that will enter the effective strength of the coupling. So remember that I told you that for an enhanced hydrodynamic behavior, we want this coupling to be rather large. And the coupling depends on epsilon r and the Fermi velocity in this way. So here, just for comparison, we have electrodynamics in the vacuum. And then here, mostly graphene in this layered structure. Then the Fermi velocity is given here, epsilon r here. And the coupling, I think the coupling that most people work with is 0.9 at the moment. And in this new proposed Scandium Herbert-Smithsonite, the Fermi velocity will be a factor 6 smaller than in graphene, and which leads to this much wider opening angle of the cone. This epsilon r is roughly in the same regime, maybe slightly larger. But putting everything together here, the effect of electronic coupling will be about 2.9. And if we take 0.9 here, then this is a factor 3.2 larger than what we have in graphene. And this will ensure this enhanced hydrodynamic behavior. Okay, so here I summarized quite a few properties of this Scandium Herbert-Smithsonite. So the copper oxide plaquettes that I showed you form this Kagome lattice. And in fact, the low energy physics is captured by a d orbital at each copper side. And I think that's quite different from graphene, where there are p orbitals. And so in this material, due to this shift, by replacing zinc by scandium, the Fermi level will be at the Dirac point, and the filling fraction will be 4/3, whereas graphene, I think it's half filling. And in fact, this orbital hybridization allows for a larger Coulomb interaction, which is confirmed by a so-called constrained random phase approximation calculation, which was done by our colleagues in Bremen that I mentioned at the beginning of my talk. And so what we predict is that alpha, so the effective electron-electron coupling, will be 2.9 versus 0.9 in graphene, so a factor 3.2 larger. And we also find that optical phonons are thermally activated only for temperatures above about 80 Kelvin. So, which makes this material very suitable for hydrodynamic behavior. So the Kagome lattice structure suppresses the formation of ordered phases. The Dirac cones, this is related to the fact that the Dirac cones are located away from half filling. And there's also another reason, which comes more from this ADS-CFT analysis, that we expect this enhanced hydrodynamic behavior because there's a critical length scale determining where there's a breakdown of the hydrodynamic scale. And this is about a factor 6 smaller in this Scandium Herbert-Smithsonite than it is in graphene. And so this critical length scale is determined holographically from the breakdown of hydrodynamic behavior corresponding to the disappearance of a purely imaginary diffusive pole. So what do I mean by this? So remember this picture where I showed you this black hole? Okay, maybe I should go back to the black hole to just make sure you know what I'm talking. So this picture. So in this picture from the gravity side, we will get so-called quasi-normal modes. So these are complex frequencies. So these are the standard normal modes you know from mechanics, but quasi-normal modes means they will be complex, so there will be some damping terms included. And of course, if these fluctuations are forced to fall into the horizon and cannot come back, then there's obviously some damping involved, okay? Because there's some loss of energy of things that fall into the black hole and don't come back. And these complex modes actually determine the poles of the Green's functions that we calculate in this ADS-CFT analysis. So there's a very nice relation between the frequency behavior of these gravity fluctuations and the poles of the 2-point correlation functions, and so of the retarded Green's function. And so these poles are actually, there's a leading pole, which is on the imaginary, which moves on the imaginary axis. And at this critical scale, it separates into two and moves off into the complex plane. And then there will be some damping involved, and there's more than just this purely imaginary diffusive pole, which means then there's a breakdown of hydrodynamic. And since this length scale is much smaller now in this new material than in graphene, we expect hydrodynamic behavior to persist to very low temperatures. So this means we predict this Scandium Herbert-Smithsonite to be a candidate to test universal predictions from holography, such as the shear viscosity over entropy density. All right. Now I move back to ADS to explain how we now calculated corrections to the coupling. But before I move on, is there any question at this stage?
Yes.
Yeah.
So when you replace the zinc by the strontium, you
Scandium.
Sorry?
Scandium, not strontium. Scandium.
Scandium, yes.
Yeah.
But anyway, so you move the Fermi surface to the Dirac point. Now,
Yeah.
of course, when I think of a material, then presumably that doesn't work that nicely, or whatever, there are boundaries, impurities, God knows what. So you will presumably end up not being precisely at the Dirac point. And how relevant would that be for the theory you present?
Well, okay. So, I mean, first of all, I should definitely agree that, I mean, of course, we don't know if it's possible to make this material, and it's a pretty drastic thing that you have to do it, and you want to have it in a certain purity and so on. And okay, I agree it's not super likely that this will just work in a very simple way. Towards the end of the talk, I have a few more examples. So one answer to your question is I'm showing this as a kind of example where you do something simple and get some interesting behavior. But there could be other materials where this works even better. Okay, so and I'll discuss one at the very end of the talk. Then, of course, if for this Dirac material, then we have the advantage that we can use this relativistic structure that I'm discussing here. Of course, if we are more in this regime, then it becomes significantly larger to apply these calculations. Of course, if the level is somewhere here, then we just get massive fermions, and there should be still something which could be seen. But if we are really below the point, I don't think it's so easy to make some predictions in the way that I'm discussing here. So I think the answer is it remains to be seen. I mean, if there's a small error, I think, you know, because we have some rather universal results, I'm still confident that something will be seen. Nevertheless, it would be nice to really have a Dirac structure to have this relativistic behavior at hand. This said, I should say there's also non-relativistic examples of ADS-CFT where one could do a similar analysis. So it's not an absolute drawback, but still it would be nice to have a structure of this type. Okay, so maybe the second answer to your question will be postponed to the end, because I have another slide about some other materials that could be relevant. Okay, so I would like to suggest this more as an idea of a material where you could do these nice things, but maybe there are other materials where it works even better, because we want strong coupling and we want a Dirac behavior. And we want this behavior at strong coupling. Yeah, so this is the idea.
Thank you.
Okay, anything else? All right, so let me move on.
Johanna,
yeah.
May I allow to add just a comment from the condensed matter perspective to the previous question?
Sure, go ahead.
Sorry, so I think that what we are suggesting here is not introducing disorder, okay, to push the Fermi level to the Dirac point. So this is a 100% substitution of zinc with scandium. So if this will ever be synthesized, will be an ordered system, not with disorder.
Yeah, thanks, Domenico. Yeah, that's of course important.
Now, since we had this comment also from the referee side, so
okay, yeah, sure, yeah, I should have mentioned. Okay, so yeah. All right. So now let's move on to the calculation which we present from the holography side now in this paper. At recoupling, as I said, and I discussed this result of Lars Fritz and collaborators, the leading behavior of eta over S is with 1 over alpha squared. But now, if we start from holography, we come from the other side. So we have this result really for alpha, more precisely the 't Hooft coupling going to infinity. And as I will now discuss from some gravity argument, the leading correction is going to be of this type with an alpha to the 3/2 here as a correction to the infinite coupling result. Now, the problem with any corrections to this result, so this result has this nice universal behavior. It does not depend on any model parameters, just on these constants, and so it's really a universal prediction at infinite coupling. But as soon as the coupling enters, also non-universal behavior will set in, and this is very hard to get under control in the ADS-CFT correspondence. And so we're actually pretty ignorant about what exactly the coefficient of this correction is going to be. So we took a rather simplistic approach and said, okay, let's vary this by 4 orders of magnitude and see what happens. And the interesting result is that not much happens. Okay, so this is what I'm going to show next. Okay, so here you can see the calculation that we did on the gravity side. So as I mentioned before, we start with the same Einstein-Hilbert action, which gives this 1 over 4 pi result, and which is linear in the curvature. And then, so now we allow for higher order corrections. So curvature squared, curvature cubed, curvature to the 4th, and so on. Now, since this Scandium-Herbertsmithite is a material in 2+1 dimensions, then this ADS dual, which is in 1 dimension higher, will be in 3+1 dimensions. So this will be an integral in 4+1, in 3+1 dimensions. And so then we can use a few nice features of gravity in 4 dimensions to analyze the coefficients of this coupling. So the first term is that first statement is that anything that's going to be of order curvature squared in 4 dimensions is actually topological in the sense that very much as the same way as you know topology from a topological insulator, but there you integrate over the field strength, and here we integrate over the curvature squared. But it just, the fact that it's topological means that if you integrate over this term, you just get a number, which is determined by the number of holes in your surface. But since here our surface is just flat and there are no holes, the number is actually 0. And this is also a non-dynamical term. Okay, so this doesn't contribute to anything propagated in this space. So there will be no corrections of order r squared. And then we went back to some rather dating back supergravity papers to analyze the terms which are order r cubed. And in those theories of supergravity that arise in the ADS-CFT correspondence, these terms are actually absent. And so the first term, the first relevant order that contributes is terms that are of 4th order in the curvature. And then if you analyze them, you see that the coefficient of these terms will be of order lambda, which is again is the 't Hooft coupling to the power minus 3/2. Now the 't Hooft coupling involves n, so the rank of the gauge group, but this rank of the gauge group we just absorb in this coefficient c, and then such that the effective electron interaction appears here. And as I mentioned before, so this correction will be model dependent, and this model dependence, we have very little control, so we parameterize this by varying the coefficient c, and we just vary it over an enormous range of 4 orders of magnitude. Okay, and then this is the picture which is shown in our paper. So let me explain all the features of this picture. So in this scale, we have the effective electron coupling. And here we have eta over S, which is our shear viscosity over entropy density in units of h bar over 4 pi k Boltzmann. And so this red dashed line is actually the leading order result where we just have 1 over 4 pi. And since we divided by 4 pi, it just at 1 here. Then here we show the kinetic theory result, which is valid at perturbatively at weak coupling and goes with alpha to the -2, just to give you a reference. And so the important new result now is this blue band. So in the limit of infinite coupling, we know the coupling, the shear viscosity over entropy density will be 1 in this normalization chosen here. And now if we assume this dependence with alpha to the -3/2 that I introduced you before, then the blue band is obtained by varying the C over 4 orders of magnitude. So for this variation, we get not a lot of variation for eta over S. And especially in this range of the Scandium-Herbert-Smithsonite effective electronic coupling that we calculated. Remember that I told you the result that we found was about 2.9, whereas for graphene, the result is about 0.9. So graphene will be about here and Scandium-Herbert-Smithsonite will be about here. And then we see that compared to graphene, this eta over S will already be significantly suppressed if we are in this region here. And also the possible variation here in graphene is much larger if we include these corrections from holography. Okay, so the upshot of the paper is that if we manage to synthesize such a material that has a coupling which is about 3 times larger than in graphene, then we will be much closer to this holographic value of eta over S. In fact, the variation is not expected to be very large compared to the result at infinite coupling. Whereas in graphene, we still expect quite a large range that is possible. So that's essentially the upshot of this figure. Okay, any questions? Okay, I don't seem to be any. So let me move on. And so the next interesting thing is that we can actually calculate the Reynolds number from this value of eta over S. So the Reynolds number is a quantity that enters the Navier-Stokes equation as shown here. So with the median of the velocity, pressure. And so here, this is where the Reynolds number appears. And actually one can show that in a wire of with W, this is the result for the expression that gives you this Reynolds number here, where this U is a typical velocity, which is enhanced at strong coupling. And then you see that eta over S here enters with a negative power. And also the Fermi velocity is in the denominator. And then you see that if this eta over S is decreased, then the Reynolds number will significantly increase. And that leads to this word turbulence in the title of our paper, because for a turbulent system, the Reynolds number must be of the order 1,000. And so in graphene, I think there were some papers about this, and it's just reaching some kind of pre-turbulent regime there. But now in this Scandium-Herbert-Smithsonite, the Reynolds number would be a factor 100 larger than in graphene. And then it really reaches the turbulent regime. And so that would be super interesting if we could see some vortices forming in the electron fluid, of course. And so this is a very nice property that this material would have. Okay, and there was a question earlier about, is it possible to synthesize this material and so on? Okay, so let me also refer to another paper also with Domenico about some other materials where such behavior could possibly be seen, which are so-called copper-based metal organic frameworks. And so these are organometallic hybrids and exhibit strong electronic correlations. but I think some variants of them have already been synthesized experimentally. So this is maybe another arena where such materials could actually be realized. Okay, so that brings me to the end of this discussion of this paper that gave the title, and I think I'm almost out of time, but let me very briefly mention those papers, which I think David explained to you already in March. In this series of paper, we investigated this Poisson flow behavior if we have a quantum wire and a hydrodynamic fluid moving in this quantum wire. And so as in the Gauge effect that I mentioned at the beginning of the talk, we indeed see this decrease of the differential resistance with the applied current. And so, of course, the weaker, the smaller eta over S is, then the smaller the resistance is overall. But we clearly see this this nice fall off consistent with the Poisson flow. And so together with David and some other collaborators, we investigated the velocity profiles in wires. So now this is the width of the wire, this is the velocity field. And there you can also see the smaller eta over S is the faster the fluid is going to move. And also, then of course, the transport will be much more efficient. And so this is interesting because now some people start to measure actually the velocity profiles in wires. And so there's especially this paper by Supizio, but I think now there are more already of these paper, and they have an experimental observation of the Poisson flow in graphene, which looks very similar to what we calculated. And just to conclude, let me briefly mention this paper with Evelina Hankiewicz and her group, which I think was also discussed already by David in March. And so this is the same setup, a wire geometry, but now we also apply a magnetic field. And then we solve the Navier-Stokes equation and look at this competition of the Hall effect and the whole so-called Hall viscosity. So if we apply a magnetic field, then we break, of course, parity symmetry, but there's also this hydrodynamic expansion that I mentioned earlier can also be established for broken parity. And then there's other transport coefficients that appear, in particular the so-called Hall viscosity, beta 8, which you can see here, for instance. And what we found there was this very interesting competition between the standard Lorentz voltage drop, so the standard Hall effect, on the one hand side, and the behavior of the whole viscous behavior of this electron fluid in the presence of the magnetic field. So in this case, parity is broken, but this whole viscosity is actually also, again, it has some topological nature. So it's a non-dissipative transport coefficient. And so here we investigated the different colors are for different boundary conditions of the fluid profile given by the so-called slip length, which you see here. And just to focus on the red curve for now. So here's the applied magnetic field, and this is the voltage drop across the channel. And then there's actually a critical value of the magnetic field where there's an exact compensation between the standard Hall effect and this Hall viscosity, which is this hydrodynamic effect. And they have different signs, so they cancel. It's in particular magnetic field, which is another interesting prediction of this hydro behavior in wires. Okay, so that brings me to the end of the talk, and let me just briefly summarize. So we investigated this Scandium substituted Herbert Smithsonite, and we predicted an electronic coupling of alpha equal to 2.9. So this is a factor 3.2 larger than in graphene. And so this, if this can be synthesized, then we may reach a region of robust hydrodynamics in solids and even turbulence, because the Reynolds number will be sufficiently large. And in particular, also a much smaller ratio of this eta over S, shear viscosity over entropy density. So in some other projects, we also investigated the Poisson flow in wires and found essentially that strongly coupled fluids flow faster. And in the final project that I briefly mentioned, we saw this cancellation of the Hole viscosity induced voltage with the standard Hole voltage. So this concludes my survey of some rather interesting predictions in effect coming from combining ADS-CFT and condensed matter physics. And so I thank you for your attention, and I hope there will be some questions. Thank you very much.
Thank you very much, Johanna. First of all, thanks for the very clear and interesting talk. Also for the excellent timekeeping. It was, I think this was the best hour we had so far. Like, so yeah, there I'm expecting questions here. So who wants to go first? Okay, I don't see anything right now, so let me maybe ask the first question. And I'm not sure, the first question might actually be more for Domenico than for you, because he's the material guy. But,
yeah, exactly.
When you showed the dispersion, like you had the Dirac cone, or this Dirac cone, and there was also this band with the hump underneath. So if I do a pure tight binding on a Kagome, if I remember correctly, you get essentially the Dirac cone, and then you get a flat band on top. So I'm guessing this band with the hump is the remainder of the flat band. So is it easy to understand why it's on the bottom?
Okay, Domenico, I think you should.
Is the sign of the hopping. If you change sign of the hopping, the flat band go to the bottom. Okay, but this is indeed the remainder of the flat band. Yes, and it's somehow not flat, but as a finite dispersion since you have longer range hopping in realistic materials. Okay, top. Good, thanks. Are there further questions?
Maybe I would like to follow up on my earlier question in a maybe more general setup. Namely, is it possible to quantitatively, or at least to get some idea about what will happen with perturbations around this idealized system? For example, so you study here a Kagome lattice, so you have a two-dimensional system. So I suppose that in reality you would have kind of stacks of 2D material, of 2D sheets, which are weakly coupled, and that weak coupling will of course introduce some energy scale and somehow disturb the results you present. Is there any?
Well, but that would be similar to graphene, no? I mean, in graphene, the same problem will arise because, I mean, with graphene, I mean, I think I showed, I mean, I think there's this, it's placed on this boron substrate, isn't it? Let me just show quickly. No, I went too far, sorry. This, yeah, okay. So I think also for hydrodynamic measurements in graphene, it has to be placed between the substrate. And so there, I really imagine that we wouldn't have a much different problem to what's going on in graphene. Well, I mean, I think what I tried to argue was that for various reasons that combine, I mean, you know, the Kagome structure, the strength of the coupling, and so on, this should be a rather robust behavior also across a rather wide temperature regime. So if it's really possible to make this material in a rather pure way, you know, I expect that these perturbations shouldn't really disturb this this rather universal feature that we are investigating here. So that I mean, I think that's the upshot, that the quantity we are looking at should be rather robust against any perturbations that you could conceive. And certainly this fact that you have different layers, this won't be very different from investigating hydrodynamics in graphene. And so I'm confident that we could see something interesting there. I mean, I wouldn't worry so much about this coupling, the X that I mentioned. I mean, I think the bigger problem is what we mentioned earlier. I mean, is it really possible to make this material by really substituting absolutely every zinc by a scandium atom? I mean, is this going to be a feasible thing to do to get a stable material? Okay, I'm not a chemist. I have no idea. Okay, but I think that seems to be an issue. But I think the purpose of this paper was more to make a suggestion for a material which is Kagome, Dirac, and also has this much stronger coupling than graphene, which really seems to be the absolutely vital point for seeing this interesting hydrodynamic behavior, such as turbulence and so small eta over s and so on. And of course, there might be other materials. I mentioned these few copper organic compounds at the end, where there's a better chance of realizing this than in this particular scandium substituted Herbert-Smithsonite. But okay, so I mean, I think the message is, there should be chances to have these materials with Kagome structure, Dirac cones at strong coupling, and still, be able to. I mean, then the hydrodynamic structure should be much more robust than a recoupling, and then I would expect that all these perturbations, defects would have a less effect than in graphene, for instance. So that's the upshot, the message.
Okay, thanks.
Johanna, can I?
Sure. Oh, hello.
Hi, Johanna. Thanks for this nice.
Nice to meet you.
Nice to see you. So, I was wondering, why do you need the Kagome lattice structure? So does it in some way protect the existence of the Dirac points? Does it?
Yeah, I think, yeah, that's, okay. The Kagome lattice structure, yeah, okay, so there's a few points here. So because there, it has all these nice properties which you know much better than me. Oh, sorry. Then it really, I mean, okay, so we are looking for something which has really robust hydrodynamic behavior. And of course, there could still be other materials where this is also possible, but we just point out that with this Kagome structure, because I think one important point is that the Dirac cones are located now away from half filling, which is different from graphene, and also because these d orbitals they necessarily lead to this strong coupling. I mean, I think that maybe Domenico can comment a little more on this, but this is absolutely vital for the strong coupling, is that you have these d orbitals, and they are of course present.
One question that arises, as you know, in graphene, the Dirac point will be destroyed by spin orbit coupling.
Yes,
right?
exactly.
Effect. Well, now, does this happen in this case as well? So here there is much heavier stuff, right? So
I would say no. I think that was one of the reasons for proposing this material, because the Dirac cone is away from half filling, then this problem shouldn't arise, as far as I understand. Yeah. Yeah, that's one of the central features of this idea. Yeah.
I mean, I also have a question about this. Like, I mean, you're saying it's away from half filling, and that's probably important for local interactions, for Hubbard type interactions and magnetic instabilities. The thing I'm wondering about is whether in your setup, there's not such a thing like an alpha that is too big, because this is something that has been discussed in the context of graphene quite a bit, which is the so-called chiral symmetry breaking. Which is an instability which comes from, I mean, okay, first it's an like in graphene, like due to the long range Coulomb interaction, there's an instability which you can, for instance, picture as a charge density wave. And this is driven by alpha, by the fine structure coupling, and okay, and then this is the part where there's not so much consensus on, but like some authors say that there's a critical alpha which is on the order 1.5. And then there's also other papers which say there's no critical point. So I'm not 100.
Yeah, okay.
Like
yeah, I'm really not an expert on this, but I really think that this fact that we are away from half filling should remedy these issues, and such that we can have really big alphas without running into all these problems that you just mentioned, and which is then again related to this Kagome structure. I think that was the idea.
Okay. Because I mean, there's just one comment there. It's also in large N. It is known that there's no phase transition. This was shown by Son, whereas for finite N, starting from a critical N, there is a phase transition. Yeah, exactly. Or at least there is a belief. So, but you're saying you don't expect this to play a role here because of the filling.
Yes, exactly. Yeah, okay. Of course, I mean, there's one issue. I mean, one question is, what exactly do you mean by N? I mean, maybe we mean... I mean N
is number of Dirac fermion flavors.
Okay, yeah, so in our case, the number of Dirac fermion flavors is 4, I think. Okay, but okay, it's important that this is bigger than 2. And so then this gives you some hope that this will lead to increased stability against these phase transitions. But I think then the Kagome structure has a much bigger effect.
Okay.
May I ask a question?
Yeah, sure.
Sure.
Hello. Hi. Nice to meet you. Hello. Yeah.
Hello. Thanks for this talk. So you estimate the strong coupling alpha based on the bare Coulomb interaction, right? I mean, you basically saw that the Fermi velocity is smaller by a factor of 3. The question is, if you go to a new material, whether the screening behavior would also change, such that you will also have a big reduction in Coulomb interaction, and then effectively the alpha would be small again. I mean, just to give one example, you would imagine that in twisted bilayer graphene, the velocities there are way smaller.
Exactly.
They are more interacting system, but they are not as interacting as you would expect, because also screening goes up a lot, because you have all these very close bands that are acting as a dielectric, and they induce screening. So the question is if you can estimate how alpha takes this into account.
Yeah, of course, first of all, this is a very good remark, and I should say, okay, I mean, I mentioned that saying that this opening angle is very important, as you just said, for the Fermi velocity and the alpha we consider. And then you could say, okay, if I go to twisted bilayer graphene, then the coupling should be infinitely strong. But then, I mean, the problem with that is also that then we leave this relativistic regime. I mean, we still require a Dirac point. I mean, if we have a flat band, then this whole construction is not going to work.
So if you don't go exactly to the magic angle, if you are close to the magic angle, you still have a nice Dirac point, and you can do all this construction. But there the alpha is not infinite, it's finite, because the screening takes over in some sense. So that's something that you should also take into account.
No, I totally agree. I don't know, Domenico, do you have any comment on this?
Can I comment?
Yeah, sure.
Actually, you mentioned, Johanna, you mentioned the constraint RTA, which is a technique that we use to take into account exactly the screening. And it's also in the table that you have shown. Okay, we computed the electron constant. So basically, we compute the screen Coulomb interaction, not the bare Coulomb interaction. So all the numbers that Johanna gave are for the screen Coulomb interaction. We have epsilon r in this table. Essentially, as you said, we compute the screening from the all other bands, not the Dirac state, but all other bands, and all these bands screen the Coulomb interaction, and we remain with an effective screened, what we call this constraint somehow interaction.
I see.
Yeah, thanks, Domenico.
Thanks.
Okay.
Yes, thanks for the question.
Are there further questions? It doesn't seem to be the case. So yeah, let me thank Johanna again for a very nice and interesting seminar. And yeah, see you.
Yeah, thanks for inviting me. Yeah.
Thanks for.
Yeah, I hope to see you all somewhere in person in the not too distant future. Yeah.
I hope so too.
Okay. Anyway, thanks for the invitation, and I certainly spread the word about the seminar, and there will be more people from Wuerzburg tuning in. And thanks a lot.
Great.